Good morning, students. Can you all see my screen?
Yes, madam.
Yes, madam, we can see.
Good morning, students. Can you all see my screen?
Yes, madam, we can see.
Yes, madam.
Okay, right. So we were talking about the simple linear regression model, and then we discuss about an alternative form of the simple linear regression model when you have only one variable. And then this is where we stop. So we were about to discuss about the analysis of variance, which is also known as ANOVA. So if you look at this diagram, now if you can, now you can see this red color line. So this red color line indicates the fitted regression line for a given data set. That is, now when we are given with the data set, we know how to find beta naught, we know how to find beta 1, and then we know how to come up with the fitted regression line. So that fitted regression line gives you the estimated values for each and every observation of your response variable. So which is denoted by yi hat. So this red color line is the fitted regression line. And also for any given data set, we can find the mean value of your observation. So we can find the mean value of the response variable as well as the mean value of the independent variable. So in this case, if you take the mean value of the response variable, your y variable, which is denoted by y bar. So since the mean is a constant value, we can denote the mean value from this green color line, right? So let's imagine our mean value for the y variable. It's somewhere here. Okay, so if you select a value, any observation, any value of your response variable, let's say it's yi, right? So if this yi, if the original observation of yi is here, we can observe there is a difference between the mean value of y and the true value, the observed value of y. Right, so that is the difference between this green color line and this observation of yi. So this difference, that is the difference between the original observation yi minus its mean value y bar. So this whole difference we can write as yi minus y bar. So if you look at from the other side, now this whole difference we can just divide into two parts. If you take the difference between this observation and this red color line, so observation is yi, the red color line is yi hats, the estimated values, the fitted line. So that I can write as yi minus y hat. And then again, this red color line and the difference between the green line. So that is y hat minus y bar. So we can see this, the whole difference, the difference between your observation and mean value, yi minus y bar, that is equal to the difference between yi minus y hat plus y hat minus y bar. Right? So that is the difference between your observation and fitted line plus difference between the fitted line and the mean value of y. So if you write this as an equation, we can write it yi minus y bar is equal to yi minus yi hat plus yi hat minus y bar. So this is what we can see from the diagram as well. Now what we are going to do is we are going to take the squared summation of the both sides of this equation. So if you take the left hand side, you have yi minus y bar. So we can take the squared summation value. So what we can do is we have to take the squared summation value of your right hand side as well. So when you take the squared summation value of the right hand side, we get the squared summation of this first term, yi minus yi hat squared summation, and the squared summation of the second term, yi hat minus y bar squared summation. And then we have 2 times summation of this, summation of the multiplication of these 2 terms. But we can prove that the summation of these two, the multiplication of these 2 terms, that is adding up to 0. The product of these, if you take the product of these 2 terms, and if you take the summation, that summation is adding up to 0. So we can omit the middle term. So that is, we will prove it later on. So that is, we have 3 terms. We are left with these 3 terms. On your left hand side, you have yi minus y bar squared summation, that is equal to yi minus yi hat squared summation plus yi hat minus y bar squared summation. So if you look at your left hand side, where you have only 1 term, so what we are doing is we are taking the deviation of all the observations of your response variable from its own mean. හැම y variable එකක්ම යාගේ mean එකෙන් අඩු කරලා squared value එක අරගෙන ඒ ටිකේ summation එක තමයි ගන්නෙ. So if you take the difference between all the observations of your response variable with its mean, right? And if you take the squared summation, this term we call as the sum of squares of total, or sometimes we can call it as total sum of squares. Now in different reference books, you can see these terms, different terms. So you can use whatever the term that is familiar with you. You can call this as total sum of squares or sum of squares total, right? So we can denote this using TSS, that is to denote total sum of squares, or else you can denote it by SSTO, sum of square total, whatever the notation which is easy for you, you can remember. Now here I have denoted this by using TSS, that is total sum of squares. And then if you look at your right hand side, this term we have, what we have done here is you have taken every observation of your response variable, and we have taken the difference between our fitted regression line. We have taken the difference between the fitted value, right? So if you take the difference between your observation with the fitted value, this term we have actually discussed earlier. This is actually the residuals, right? We have observed when you take the difference between your actual observation and the fitted value, we call it as the residual. And we have also seen when you take the summation of these residuals, they are adding up to 0. So in this case, what we have done is we have taken the squared value of this residual and we are taking the summation. So then it's not adding up to 0. අපි residuals ගත්තාම residuals වල අපි ගත්ත summation එක 0 වෙනවා. ඒක නිසා තමයි අපි මෙතන squared values අරන් තියෙන්නේ. හැම residual එකම square කරලා ඒ ටික එකතුව. එතකොට summation එක 0 වෙන්නේ නැහැ. So you can see now in this case, this is known as the error sum of squares, because we are taking the summation of the squared value of the error. So we call this as error sum of squares, which is denoted by ESS, or in some books they have denoted this using SSE, which is known as sum of squares of errors. So whatever the term you can use, whatever the term you like. And then if you look at the other term, then you have yi hat minus y bar squared summation. So yi hat is the fitted value. From each and every fitted value, you have to subtract the original mean value of your response variable. So this is known as the regression sum of squares, which is denoted by RSS, or sum of square regression, right? So here we can find this sum of square error, sum of square regression, and sum of square of totals using these equations. And we can say this total sum of square is equal to regression sum of square and error sum of square. So we can actually write at the end, our total sum of square is equal to error sum of square plus regression sum of square. Now, when you look at these terms, so to calculate these values, these sum of squared values, anyway, we have to come up with our fitted regression line, because you can see you have to anyway calculate yi hat values. So the yi hat values, they are coming from the fitted regression line. So we have to anyway estimate the beta naught value and the beta 1 value. So in that case, without fixing to this equation, there is an easy way to find out these three terms. That is, we can anyway, we can calculate the total sum of squares by SYY. That is, when you take the deviations between the original y, subtract its mean, take the squared value and the total. And if you are planning to calculate the regression sum of square values, what you can do is you can take SXX, because anyway we are calculating SXX when you are calculating the parameters, right? And then we can multiply this by beta 1 hat squared value. Right? And what here important is, since our total sum of square is equal to these two terms, and if you know the total sum of square and if you know the regression sum of square, by taking the difference, you can find the value of error sum of square. Or else you can go to this original equation, that is yi minus yi hat squared summation. You can calculate the error sum of square as well. Now, when you calculate these three terms using your given data set, we can construct this table, which is known as the Anova table. So if you look at this table, you can see the first column, it says source of variation. Now we saw when you take this data set, we can see a difference between your original observation of your response variable and its own mean. So that is the total variation. So that is what we have denoted by the total. That source is the total variation. And we saw this total variation, we can divide into two parts, which is coming from the regression line and which is also coming from the error term. So here, the first variation is coming from the regression and the second variation is coming from the residual, so from the error term. So then what we do is, in the second column, you can see the second column is known as the sum of squares. In sum of squares, we have to calculate the respective sum of squares of each source of variation. So for the regression, we have to calculate RSS, that is regression sum of squares. For the residual, we have to calculate error sum of squares, and then we can take the total and calculate the total sum of squares. And then if you look at the third column, we have a column which is known as degrees of freedom. Right? So here, since we are talking about the simple linear regression, which we have only one independent variable, in this case, the degrees of freedom which is associated with regression is 1. So actually this number, it's coming from the number of independent variables you have in the system. So since you have only one x variable, here it's 1. But you will see when we discuss the multiple linear regression, this number is changing. When you have more x variables, you have to denote that number. That is, when you have 2 x variables, you have to take this value as 2. Since we have only 1, we have denoted this value as 1 for the simple linear regression. And then if you take the number, the degrees of freedom, which is associated with residuals, it is n minus 2. So n means the number of observations you have in your data set, and minus 2, why we have taken 2 here? 2 is the number of parameters you have in your model. So in simple linear regression, we are estimating 2 parameters. That is, we have beta naught and we have beta 1. So that's why we take the number of the number of observations in your sample, and we have to subtract the number of parameters in your data set. So that is n minus 2, since we have 2 parameters in simple linear regression. And then what we saw earlier was, now these RSS and ESS, these two terms are adding up to the total, right? The total sum of square, that is equal to the summation of these two terms. So it's same as the degrees of freedom. You can obtain the degrees of freedom which is associated with the total by adding up these two values. So that is n minus 2 plus 1, which is adding up to n minus 1. Okay, and then we have so we have the sum of squares values, the degrees of freedom, and then the next column is the mean square values. So mean square values you can calculate by taking the by dividing the sum of square values by its own degrees of freedom values. As for an example, now in this case, from the regression, you have regression sum of square. If you divide it by its degrees of freedom, so in this case, it's 1. So we will get the sum of mean square regression value, right? So this is denoted by mean square regression, MSR. Or in other way, you can denote it by regression mean square, that is RMS. And when it comes to this one, here the source is the residual and we have the error sum of square. So what we can do is we can take the error sum of square and then we can divide it by its degrees of freedom, that is n minus 2. So this is equal to mean square error. Or you can denote it by SEM, right? So you have the mean square error and the mean square regression. And for the total, we are not interested about calculating a mean square value. And then what you have to do is you can take the, again, we can take the ratio, we can divide these two mean squared values, and then we can obtain this F value, F statistic. So here what you have to do is you can take the mean square regression, you can divide it by mean square error, right? This is same as RMS, EMS, that this is regression mean square, error mean square. You can use whatever the notation. So I have shown you both notations. You can select whatever the notation that is easy for you. So here we have come up with the F value, F statistic value. So this is how we construct the Anova table. So after constructing the Anova table, by looking at this F value and by comparing this F value with the table F value, we can just identify, or we can just evaluate the accuracy of our model. How whether our model is a significant one or not by looking at this value, right? So I will show you how to do the calculations, but in this case, actually, now when we were discussing about developing the confidence interval and how to do hypothesis testing using beta naught and beta 1. So the same thing, to check the accuracy of the model, whether your model is a good fit, we can conduct the hypothesis testings for beta naught and beta 1. So in this case, when it comes to the simple linear regression model, by constructing an Anova table, you can't do anything new. So, but the concept is important, because when it comes to multiple linear regression, the ANOVA is something really important. So in this case, when it comes to the simple linear regression, we are just explaining about the concept, but we will see how to apply and how to get into the conclusions, how to check whether your model is significant or not, to do something different when it comes to multiple linear regression. So let's see how to do these calculations, how to construct the Anova table. Okay, so actually this is what we discussed in our last lecture. So we have this data set, and using the matrix form, we found the regression line, right, using our data set. And in this case, if you take okay, so this is our original data set, and then here we have calculated x minus x bar values, and then I have calculated the x minus x bar squared values, y minus y bar values, and y minus y bar squared values, and then I have taken the totals as well. Here you can see. So if you look at the first, the value, that is regression sum of squares, right? The regression sum of squares, actually we can take, if you know the beta 1 hat value squared into SXX. This is how you calculate the regression sum of squares. Now in this case, if you can remember the beta 1 value that we calculated using our data set, I think it's minus 0.09 as based on our data set. So I'm not going to calculate the beta 1 value again. So let's take our beta 1 value as minus 0.09. Just assume this is our beta 1 value. So this is the slope. And then what you have to do is to calculate the regression sum of squares, that is RSS. What you have to do is we can use this equation. So that is, we can take the squared value of our beta 1 coefficient, beta 1 parameter, and then multiply that with SXX. So SXX means xi minus x bar squared summation. So this column gives you x minus x bar squared values, and the summation is this. So here I'm going to calculate the regression sum of squares. So that is, I have to take the beta 1 value, the squared value of beta 1. So beta 1 into beta 1 into SXX. So this one. So then we can see the regression sum of squares is equal to 24.35. And then let's calculate the total sum of squares. So that is very easy to calculate because we can see the total sum of squares is equal to SYY. So in other words, that is y minus y bar squared summation. So I have already calculated that. So that is total sum of squares, which is equal to this value, that is 29.8. And then we are left with this error sum of square value. So error sum of squares we can easily take by taking the difference between these two values. That is, from the total we have to subtract the regression sum of squares, since the total is adding up to regression sum of square and error sum of square. Right now in this case, we can complete our Anova table. So I will just copy this Anova table, copy it here. And then now you can see we have calculated these terms. So I'm just removing these equations. Okay, now here what we can do is, now for the regression sum of squares, we have this value that is 24.35. So we can put it here. And for the error sum of square, that is the difference between the total and the regression, we have it here. And for the total sum of squares, we have 29.8, this one. So we can complete the Anova table by putting this sum of squares values. And then we can insert the respective degrees of freedom values as well. So when it comes to regression, we know since we have only one independent variable, the degrees of freedom should be equal to 1. And when it comes to residuals, the degrees of freedom should be equal to n minus 2. Now in our data set, if you check here, we have 10 observations. Since we have 10 observations, n is equal to 10. So 10 minus 2 is the degrees of freedom here. And then for the total, that is n minus 1, that is 10 minus 1, or simply it's equal to the total of these two degrees of freedoms, that is 9. And now we can calculate the mean square values. So the first thing, we can calculate the mean square regression, MSR value. So you can take it as RMS. And then we can calculate the error mean square value. So in this case, first, if you calculate the regression mean square, that is, we have to take the sum of square regression. That is 24.35, and we have to divide it by the respective degrees of freedom. In this case, it is 1. So you get the same value as the regression sum of square for the regression mean square value. And when it comes to the error mean square, the error sum of square is this. You have to divide it by the degrees of freedom. In this case, it's 8. And then you get a different number for the error mean square. So we have the mean square values. And then what you have to do is we have to take the we have to divide the regression mean square value by the error mean square value to find out the F statistic. So you can see in this case, our F statistic is 35.79. So this is how we construct our Anova table. So for this given data set, this is our Anova table. So I told you, now by looking at this F statistic, we can just come up with the conclusion whether our model is significant or not, right? So in this case, our model is significant if the calculated F value is larger than the table F value, right? In actually what we are testing here is in the simple linear regression with the Anova table, the hypothesis that we are testing is whether beta 1 equal to 0 versus beta 1 not equal to 0. So if your fitted regression model is a significant one, there should exist a beta 1 value, right? So that is, we have to come up with the conclusion that beta 1 is not equal to 0. That is, you have to reject your H naught, null hypothesis. In that case, you can reject your null hypothesis when the calculated F value is greater than the table F value. So I will write here, in this case also, we are testing H naught, that is our beta 1. This is equal to beta 1 equal to 0. And here H1 is, we are testing whether beta 1 is not equal to can take beta 1 also from here. Right, so our H naught is beta 1 equal to 0 and our H1 is beta 1 not equal to 0. So what you have to do is here you can reject your H naught value if your table, if your calculated F value, this calculated F value is greater than table F value. This is what we do in simple linear regression. This is the hypothesis that we are testing. So nothing new. We can actually do this even without constructing this Anova table, but just we want to illustrate the concept of Anova here. Now for this data set, we can see our calculated F value is 35.76. So let's check with the table value. Okay, now in that case, when we are checking the table value, when we check the F table, you will see, I will show you the F table. There are two things that we have to check. We have to, when you read the values from the F table, you have to read the degrees of freedom associated with the numerator and the degrees of freedom associated with the denominator. So in this F value, we have calculated this F value as a ratio of these two values, that is the regression mean square and error mean square. So if you take the regression mean square, which is coming from the numerator, its associated degrees of freedom is 1. And when you comes to the denominator, the error mean square, its degrees of freedom is 8 based on this example. So we can see when you take the degrees of freedom, the numerator's degrees of freedom is 1 and the denominator's degrees of freedom is 8. So we have to make sure that we are going to read these values from the table. Now let's see a table, F table. Okay, so in this F table, so you can see you have the degrees of freedom in the numerator here. So our degrees of freedom of numerator is 1. So we have to read the first column. And then if you look at this side, here you have the degrees of freedom of the denominator. So our degrees of freedom of the denominator, that is 8. So we have to check 8 from the table. So it's not here. So let's go down. Okay, see you have 8 here and 1 here. So we have several values. In this case, you can see we have so many values. So here in this test, we are taking alpha as 0.05. So we can read the value which is associated with 0.05. So that is from the table, we have 5.32 as the table F value. Right here, the numerator's degrees of freedom is 1, denominator's degrees of freedom is 8. So at the intersection point, you can read the table value, that is 5.32. So actually the calculated value we received from the data set, that is 35 point something. So you can clearly see the calculated value is very large value. So when you compare it with the table value, it exceeds the table value. So in that case, we can come up with the conclusion that we can reject H naught. So we reject H naught means beta 1 equals 0. We reject it. So that is beta 1 is not equal to 0. That is, we can come to the conclusion that our model is a significant one. We have fitted a significant model. So that's how we check the significance of the model using the Anova table. Is that clear for y'all? How to construct the Anova table and how to check these hypotheses using the table values and the calculated values using the Anova table. Is that clear? You have any questions? Okay, then I hope it's clear. So now after after fitting our regression line using our data set, now one of the main objectives why we are fitting the regression line is to forecast. Earlier also we discussed that. Now the important thing is when you want to forecast, if you want to give a forecast value, if you want to forecast your future values, then you have to make sure that your model is a good model. It's an accurate model. These predictions are accurate. So to do that, just after by finding beta naught and beta 1 value, and just after by coming up with the equations, we can't tell that go ahead and you can use this equation to predict the value. So we have to check the accuracy of our model. So in that case, we have various measurements to check the accuracy of the model. So before going to that far, the first, by looking at the model by first instance, there is a measurement that you can check, which gives the overall accuracy of the model. So we call it as the coefficient of determination, or we call it as R squared value. So R squared value means you have to take the ratio, you have to divide the regression sum of square value by the total sum of square, and then you can calculate this R squared value, which is known as the coefficient of determination. Now, in this case, if you look at this equation, so the total sum of square means that will give you the total variation, right? The variation between your original yi's with its mean. So that is the total variation. But if you look at RSS, that is RSS means the regression variation, that is the variation between the fitted value and the original mean. So actually what we do here, now in this case, if you take RSS, we know we can replace by, we can find RSS by taking the difference between the total sum of squares and error sum of squares. So if I can write this same equation by replacing RSS as TSS minus ESS. So in this case, if you just further simplify, TSS divided by TSS is 1 minus ESS divided by TSS. So you have this equation. So when you calculate the R squared value, you can simply take RSS over TSS, or if you know the error sum of square and total sum of square only, you can use this equation to calculate the R squared value. So actually this R squared value is telling you from the total variation how far your model, the variation of your response variable is explained by the independent variable, or how good or how much your independent variable, the variation of your dependent variable is explained by the independent variable. So the dependent variable is y, that is your response. So from the x variable, what we do here is, in the simple linear regression, we are going to come up with the equation where your response variable is depending on x. So we are substituting values for x, and then we can forecast. So what we are doing here is, from the coefficient of determination R square, it explains you the total variation explained by your regression your independent variable, the total variation of y explained by your x variable is denoted by this r squared value, right? So you can see, so if your r squared value is 1, that is all the total variation of y is explained by your x variable, which is the perfect case. But actually, it's not the reality. It's very hard to, actually, in most of the cases, we will never come up with the value for r squared which is equal to 1. So in most of the cases, you will see when you fix these regression lines, for the r squared value, we have for the r squared value, we have a percentage. And when you will see when we are doing the practicals also, in the computer outputs also, we have this r squared value as a percentage, right? So as a percentage, it shows you how far your x variable is explaining your y variable, the variation of y. So if you have a good value, which is actually more than 50-60%, that is your model is a good fit. Okay, and when it comes to simple linear regression, since you have only one x variable, what happens here is when you calculate this r squared value, that is same as the correlation. Now we know when you have two variables x and y, at the beginning of this course, we discuss how to calculate the correlation coefficient. So if you calculate the correlation coefficient and if you check that with this r squared value, you'll get the same value for the r squared and correlation coefficient in the simple linear regression, right? So in the multiple linear regression, that is different because there you have more than one x variable, but here it's the same. So let's calculate this r squared value for our given data set and check what we have. Okay, right. So here in this case, I'm going to calculate the r squared value. So in this case, I have the r squared value. So how I calculate the r squared value? I have to take the regression sum of squares divide by total sum of squares. So the regression sum of squares is this, and that I have to divide by the total sum of squares. So in this case, you can see it's 0.81. That is, if you convert this into a percentage, that is 81%. So in this case, the model that we have fitted, it's some for a good fit for our data set because we have a high value for the coefficient of determination. For the r squared, we have a very high value, which is more than 80%, so that our model is good. Model is a good fit. So in this case, you can just check when you're at home. You can just check the correlation coefficient of these x and y variables and check whether it's the same, whether you get the same value as 0.81 when you take the correlation between x and y. So is that clear with y'all?
Yes, ma'am.
Okay, right. So then now we discuss how to, like, we know how when the data set is there, how to find beta naught, how to find beta 1, how to do hypothesis, and how to find the confidence intervals, and also how to construct the Anova table. And there also we know how to check the significance of your model by looking at the Anova table in simple linear regression. And then we discuss how to calculate the r squared. And then again, now what we can do is now to check our model is a good model, or to check the accuracy of the model, what we have to do is we have now at the very beginning, when we are fitting these regression models, we had some assumptions. If you can remember, we said that our response variable that is linearly related with our independent variable. We are interested about the relationships where x and y are linearly related. And then when we said our residuals, the error terms are having a zero mean value, and the error terms are having a constant variance, and these error terms are normally distributed. So if we want to make sure that our model is a good fit, if we want to evaluate the accuracy of our fitted model, we have to check all these assumptions. So if these assumptions are violating, that is, our model is not a good fit. So in regression analysis, whatever the model, whether it's a simple linear regression model, multiple linear regression model, we have to check these assumptions, which is known as model diagnostics. So after fitting the regression model, we do these model diagnostics to check the accuracy of our model. So in most of the cases, to check these models, if you have a single variable, now when you are doing a descriptive analysis, if you want to check whether there is an outlier, and when you want to check the distribution of that variable, you can just use a box plot, or you can use a stem and leaf plot, right, or a time plot. But in this case, when it comes to regression, you have at least two variables. You have at least one x and one y. So in that case, we can't use those, we can't use a box plot and check the accuracy of the model. So what we do is we just take two variables at a time, and then we check these assumptions. So here we call, in most of the cases, to check these assumptions, we are using the residuals that we have obtained through the model, right? The errors that we have obtained through the model. So since we are using the residuals to check these assumptions, we call this as residual analysis as well. So after fitting the model, we have to do a residual analysis to make sure that our model is an accurate model. So when it comes to the residual analysis, now we know how to calculate the residual. Residual එක හොයාගන්න හැටි අපි දන්නවා. හැම yi ගෙම yi hat අඩු කරාම එයාගේ error term එක තමයි හම්බ. So that is, the residual is equal to yi minus yi hat. And in this case, here we are talking about two important residuals. That is, we can just take these residuals and we can conduct the residual analysis. And also in some other cases, there are another two important residuals that we can use. That is the standardized residuals and studentized residuals. When it comes to standardized residuals, what we are doing is we have to standardize our residuals. So when you standardize any variable, what you have to do is you have to take the variable and divide it by the standard deviation. So in this case, we know we have assumption that the variance of the residuals, they are equal to sigma square. Residuals වල variance එක අපි assumption එකකට ගත්ත constant variance එකක් තියෙනවා ඒක sigma squared කියලා. So actually we can show, if you take the error mean square value, which we obtain by dividing the sum of square error by its degrees of freedom, this error mean square value, this is an unbiased estimator for the variance of the errors. අපි errors වල variance එක sigma squared කියලා ගත්තොත් අපි Anova table එකේ හොයන EMS error mean square value එක මේ variance එකට unbiased estimate එකක් විදිහට use කරන්න පුළුවන්. So in that case, if this error mean square is an unbiased estimator for the constant variance, So we are interested about the standard deviation. So you have to take the standard, the square root value of EMS, and when you take the residual EI and when you divide it by this standard deviation, that is the square root of EMS, then we can standardize our residuals, right? Nothing new. What we did was we take the residual and divide it by the standard deviation. So, but we don't know a value for standard deviation. So we just use this unbiased estimator and we can take the square root value of that. And then there's another residual which is known as studentized residuals. If you want to obtain the studentized residuals, what you have to do is we have to take the standardized residuals, and then you have to again divide it by the square root of 1 minus h1. Here, this h1 is known as the leverage value. So we will discuss it later, how to calculate this leverage value. But you can use these standardized residuals and studentized residuals in order to calculate, in order to conduct this residual analysis. Okay, so now when you take the residual analysis, so by calculating the standardized residuals and the studentized residuals, what we are going to find out is we are going to check the accuracy of our fitted model. So these are the things that we are going to find. We are going to find whether the regression function is not linear, because we want to have a linear function. We are going to find whether the error terms do not have a constant variance, and whether the error terms are independent, and the error terms are normally distributed, and the model fits all but one or few outlying observations, whether outliers are there. One or several important independent variables have been omitted from the model. Now, this point, it's not coming under the simple linear regression, but when you have the multiple linear regression, we can check what happens when we omit certain variables to the model, right? So first we are going to discuss about the first 2 points, that is how to check whether the regression function is a linear one, and how to check whether the residuals are having a constant variance. Now, when you do this residual analysis, you will see, if you just check the reference books, or if you just search on Google, you will see when you plot these the residual plots, we have to take the residuals. We have to take the residuals and the independent variable or the fitted value to obtain the residual plot, right? So from the data set, for each and every pair, we have an x variable. So you have to take the value of your x variable and its associated error term, and then you can plot it. Or else you can take the fitted value. If you take the first observation, you can see what is the fitted value, and then you can find out the error term, and then you can plot it. So in this case, when you, any graph you can use, these graphs are known as residual plots. So for the residual plot, for the x-axis, you can take x, or you can take y hat values, right? But for y-axis, you have to take the error values, the residuals. So how are we going to check whether our the function is a linear function and whether the errors are having a constant variance? Now, if you look at this, now when you take our residual plot, you will see sometimes if you look at this, the last graph, you can see all the points are distributed in a constant band. if this is your case, when you obtain the residual plot, if you can see nicely all the points are distributed in a constant band, then that is, we can come to the conclusion that the residuals are having a constant variance. අපේ data set එකට අදාළව residual plot එක ගත්තාම මේ ඔක්කොම observations මේ වගේ ලස්සනට constant band එකක නම් distribute වෙලා තියෙන්නේ අපිට කියන්න පුළුවන් අපේ errors වලට තියෙන constant variance එකක් කියලා. එතකොට ඒ assumption එක හරි. But if you can see any pattern, right? There are different kind of patterns. So if you can see a pattern like this, you can see in the first graph, the residuals, you can see they are showing an increasing pattern. In the first graph, there is an increasing pattern. And here, the second one, there is a decreasing trend. So if you can observe any pattern like this, that is, our residuals are not having a constant variance. That is, it's violating, right? Our assumption is violating. So you can just check it using the residual plot. And if you look at this one, if you can see a pattern like this, you can clearly see there is a non-linear pattern in the residual plot. If you can see a non-linear pattern, that is, there is no linear relationship between x and y. So that assumption is also violating. So by observing our residual plot, we can check whether the residuals are having a constant variance and also whether it's having a non-linear pattern or not, right? So you have to take the residual plot and check it. And then the other thing is we can check the normality of the normality assumption. That is, we have assumption, we believe that our errors are independent and they are normally distributed with zero mean and constant variance. So the constant variance assumption, we just check. And to check whether the errors are normally distributed, what we can do is we can obtain the normal probability plot. So in this normal probability plot, what we do is we just take the values, and then here you can see so here what we are going to do is we assume these errors are coming from the normal distribution, and then we can calculate the expected values of this normal distribution, and then we can take the rest, the true values, and then we can plot them. So then you will have the normal probability plot. So when you observe the normal probability plot, if you can nicely see all the observations are laying on one straight line, then we can conclude by looking at this normal probability plot, our errors are normally distributed. අපි normal probability plot එකේ ඔක්කොම data points එක ඉරක් මතට එනවා නම් අපිට conclusion එකකට එන්න පුළුවන් අපේ errors normally distributed කියලා. So in that case, now if you look at this, the example that I have put here, you can see there are very slight deviations, but if you look at the graph, the overall tendency, you can see it's like almost all the data points we can take into one straight line. So that is, we can come to the conclusion that our errors are normally distributed. But if you can see so many deviations from using your observations, then that is, we cannot conclude that the errors are having a normal distribution. That is, that assumption is violating. And when it comes to this normal probability plot, these plots, you don't have to calculate or you don't have to draw them manually, because we'll be discussing about the practical and how to obtain these plots. When you feed the data set into the software, we can easily get these plots. So don't worry, you don't have to calculate manually. But in case in the exam, I can ask you to just draw the residual plot, because when you are finding beta naught and beta 1, and when you're estimating the model, we can also just plot the x values and the residuals, so the fitted values and residuals, and just we can easily get the residual plot. So that something like that is possible, but you don't have to draw the normal probability plot manually. And also another thing, now I told you when it comes to the simple linear regression, we have only one x variable, but in when it comes to multiple linear regression, we have so many x variables. Now, in that point, we can just check what will happen if we omit a particular x variable, right? And what will happen when we add a particular x variable. So in this case, when we omit or when we add a particular x variable, if the residuals are moving towards positive side or moving towards negative side, then we have to pay attention to that variable. So, but we are not going to discuss about this point here, since it's not relevant to simple linear regression. And then another point is outliers, the leverage and influence. Now, when you have a data set, right, sometimes you have extreme points in your data set. That is, for an example, if we are going to predict, let's say from your batch. Now here I have 37 students. I'm going to take your age and your weight, and I'm planning to fit a regression model to forecast your weight value using age, right? So in this case, if I take these two values, there may be some extreme point. Let's say the average weight value is somewhere around 45, but there may be a student whose weight value is equal to, let's say, 35. And there may be a student whose weight value is equal to, let's say, 80. So these two are very extreme points. So we call them as the outliers. But what happens in simple linear regression is, since we are using the least square method, if you can remember, in the least square method, what we did was, we are trying to minimize the error as much as possible, and then we are going to come up with the two parameters, beta naught and beta 1. අපි least square method එකේදී කරන්නේ අපේ error එක පුළුවන් තරම් අඩු වෙන වෙලාවට අදාළ beta naught සහ beta 1 තමයි අපි හොයාගන්නේ. So in that case, even when you have outliers, they will take those outliers into your data set and try to fit your regression line as the line goes through the outliers as well. So there is a disadvantage in that. So we have to check what will happen when you use a particular point. If that one is an outlier, what is the influence? Right? Now, sometimes if you have an outlier in the center of your observation, in the center of your data set, if you even delete that outlier, there is no much impact. අපේ outlier එක තියෙන data set එකේ මැද distribute වෙලා නම් අපි ඒ outlier එක අයින් කරා කියලා අපි කලින් fit කරපු model එකයි ඊට පස්සේ fit කරන model එකයි අතර ලොකු වෙනසක් වෙන්නේ නැහැ. But in other case, if you have an outlier which is very which is distributed in like in the two sides, and if you have a very big distance with the center point and that outlier, and if you delete that outlier and try to fit another regression model, you will see there is a big influence. There is it will affect both the slope and the intercept. So in such cases, that such outliers, they have a strong leverage on regression coefficient, right? So we have to check what outliers, what are the data points which can make a big influence on your data set or not, then we can pay more attention to those data set, to those observations, right? And in sometimes when you sometimes when you just check the leverage value, this is actually the leverage value is something which gives you a hint whether the observation is an outlier or not. And if this leverage value is a very high value, that is your observation is an outlier. So in that case, when you check this leverage, sometimes it's very a big value, but sometimes even though it's a very big value, it has no impact to the data set. We can come across with some situations like that when we are dealing with the data sets. In that case, if it has no impact on the data set, or if it has no impact on the fitted regression line, even though it has a big value for the leverage, we cannot consider that as an outlier, right? And here, if you look at these plots, if you look at these first two plots, right, you can see here you have an outlier. So here we have fitted a regression line without this outlier. We have a fitted regression line without the outlier. And if you look at the second graph, and if you look at this point, in this case, this observation is also having a high leverage value, but it's not an outlier, right? Because it's far from the mean, but it's very close to the fitted regression line. In this case, if you consider this as an outlier, if you check the leverage value, it may be a very high value, because you can, and also it's an outlier because you can see if you take the distance between the fitted regression line and this observation, that is, there is a big distance. But here there is a very small distance between this and the fitted regression line. So even though this is an extreme point, this we cannot consider as an outlier because the fitted line goes very close to this observation, right? And if you look at this one, so this is line without outlier included the small influence. So here, this is the line without the outlier. And here, when the line when outlier included, and this is the line without outlier. So you can see what happens when we have an outlier and what happens when we remove that, with how this the whole fitted line is changing when you change these outliers to fit the regression and all. So in order to check whether a given the leverage value of a given point, you can use this equation. So you have xi minus x bar squared divided by summation xi minus x bar squared plus 1 over n. So when you use this equation, for each and every observation, we can calculate the leverage value. Then we can get an idea whether that one is a whether that observation can impact our data set or not, right? So actually this leverage value HI, it measures the distance from the mean of X. You take the observation and then it measures the distance from the mean of X, right? And then if you want to take the average of these leverage values, that is, we can show, that is, we can easily calculate it as P over N, where P is the number of parameters. So in our case, when it comes to simple linear regression, we have only 2 parameters. So 2 over N, we can calculate the average of the leverages, right? And also in this case, the influence of a particular observation on the regression, it depends on both the leverage value and where that observation is distributed, or where that observation is lying. Because I told you sometimes for each an observation, when you calculate this leverage value, it's a high value, but the impact is low. Sometimes the leverage is high and the impact is also high. So by just calculating the leverage values, we cannot just consider whether this is an outlier or not. අපි observations ටික අරගෙන මේ leverages calculate කළ ඒවා high වෙන කට්ටිය හැමෝම outliers කියලා කියන්න බෑ. මොකද සමහරු high වුණාට impact එක low. ඒක outlier එකක් වෙන්නේ නැහැ. So actually we want to come up with a good measure where we can conclude whether a particular observation is really an outlier or not. So here we are calculating this Cook's statistic, which is denoted by DI. So in this, the Cook statistic is calculated as this. You can see HI over 1 minus HI into RI squared over P. So P is the number of parameters. So HI is the leverage value and Ri is the standardized residual value, right? So in this case, the Cook's distances or the Cook's statistic we can calculate by using our data set. Then what we can do is, there is a cutoff point that we can use, that is 4 over n minus p. So n is the number of observations you have, p is the number of parameters you have. So we take this as the cutoff point. So we can calculate this Cook statistic for each and every observation. And then what we can do is, we can just check which observations exceed this cutoff points, and then we can say they are the influential data points when we fit the regression line. So from that we can identify the outliers. So when we identify an outlier for a given data set, we can't just omit those outliers and fit the regression. So there are methods how to deal with outliers. We will discuss them later. But as per this course, you have to know how to identify the outliers using this Cook statistic. අපි Cook statistic එක පාවිච්චි කරලා මේ cut off point එකට වඩා වැඩි වෙන කට්ටියව outliers කියලා identify කරගන්නවා. හැබැයි outliers identify කරගත්තා කියලා එවලින් ලොකු impact එකක් තියෙනවා කියලා අපිට ඒක සම්පූර්ණයෙන්ම අයින් කරලා model එකක් fit කරන්න බෑ. අපිට outliers හරියට කොහොමද outliers එක deal කරන්න කියලා අපිට analysis වලට එක techniques තියෙනවා, but we are not going to discuss them here. So I want you to understand how to identify the outliers using the Cook statistics. So is that clear up to that point? So we will, right, I will show you from the given data set how to identify the outliers using the Cook statistic. So I'm going to stop at this point. So on Tuesday, we will discuss for a given data set how to identify these influential points, the outliers using the Cook statistics and the leverages. So if you can, I will upload all these materials now. The Cal is working. So you can just download all the materials from Cal. Okay, then we'll wrap up the session for today. Thank you and have a nice day.
Thank you, madam.
Thank you, madam.